Okay, now I've talked about work in every video so far, but this is the video that we're really going to get into some of the important aspects of work and the right ways to be using it and to be thinking about it. The first thing that I want to emphasize is the best way to figure out what work is in a system is to look at how energy changed. You're very, very often going to be given information so that you can quickly find how much kinetic energy changed or how much potential energy changed. And from there, you can know what work was done. The formula that has F times D in it, you're not given nearly as many opportunities to use, but students default to that one because it seems like, um, since it has more moving parts, it seems like it's the right one to use. So first thing that you always want to do is look at how much did my energy change? And once you calculate that, you know what the work was. But if you're not given that information and you know for sure that you're given an applied force and its displacement, then you can use this formula, F times D. When we say F times D, it has this little parallel symbol in there because we care about what direction the force is relative to the displacement. If the force and the displacement are going the exact same direction, force is this way, displacement is this way. That would be like if I'm pushing a block or pushing over Ethan or something like that, my force and the motion of our contact point are in the same direction. That means that I have done positive work on my system. That means that I have work is positive and the change in energy is also positive. So if I had Ethan and I gave him a shove, I did work on him. My force and displacement were the same way. And now he has more kinetic energy than he had at the beginning because I pushed on him. If, on the other hand, Ethan was being thrown to me and I was catching him, at that point, his displacement is towards me, but my force is in the other way because I'm trying to decelerate him. Or if I took a block and I pushed it across the ground and we had friction and it was slowing down, the friction would be towards me, but the displacement would be away from me. If that's the case, then we have the work is negative when they're going opposite directions, which means the change in energy of our system is also negative. The next option, though, and this is where students start kind of getting tripped up a little bit, is if work is this way, or I'm sorry, if displacement is this way, like a block is moving this way, and I'm holding it by a string. So like I have, I don't know, like I don't know why I would have this, but I have like a pendulum. I'm just walking sideways with it. Or if I have a cup and I'm holding the cup on my hand and I'm walking with the cup, so that the force I'm applying is up, even though the displacement of the cup is to the side. If I'm doing those things and they're at a right angle, it can't be positive because they're not going the same way. It can't be negative because they're not going opposite ways. It must be zero. So in this case, we have work is zero. That means the change in energy by that force is also zero. This leads to a lot of confusion for students because if you think about something like carrying a really heavy box like across your room, people think, oh, that would be a lot of work. It's so heavy, it would be hard to do. But from a physics standpoint, since the force that you're applying to keep it up is the force opposing gravity, you're not really doing any work other than the moment where you first accelerated it forward. From then on, from a physics standpoint, the energy of the box is staying the same. Therefore, you're not doing any more work. You could compare that to something like typing on a typewriter. When I type on a typewriter, or that's old fashioned, on a computer, on a keyboard, if I'm typing on a keyboard, I'm applying a force and the key is moving down a little bit. And every time that I push that button and I apply the force down and it moves down, I'm doing work. And from a physics standpoint, there's more work and work happening a lot more often while somebody's typing, even though that's a very easy job, than there is when you're holding something heavy and moving it around. The most common mistake with this particular problem, and the thing that they test you for all the time on the AP exam, is if you have something that's moving in circular motion, the force always has to go towards the center while the displacement is always tangential. Since they're always at a right angle to each other, nothing that's going through circular motion is having any work done on it. So remember that. If something's moving in circles, it has no work being done on it. Finally, if we have something where they're not going the same direction, opposite directions, or at a right angle, if it's going at an angle, that's where we use our final formula, where we have FD cosine theta. And if we have that, then probably if the force is going in some ways parallel to the displacement, we would have positive work being done. If the displacement is this way, but the force is back at an angle this way, then we would be having negative work done. But because not all of the force is in the same direction, this is a less efficient way. Not as much of the force is going to be transferred. And we can really say that only this part right here, this component of the force is being pushed, is participating in changing the energy, and that happens to be the cosine component. And so that's where that equation is coming from. It's the cosine component of the force times d is equal to that work. And if we have cosine of 0 degrees, that's 1, which is why we get positive work. If we have cosine of 180 degrees, meaning that the force is going to the left and the displacement is going to the right, that's -1. So we have negative work. If we have cosine of 90 degrees, it's at a right angle, which means cosine of 90 is 0, which means no work is done, and so on. So now hopefully you have some good ideas of when to figure out that works with positive, negative, or 0, and when you have to use that cosine equation. I promise it doesn't come up that often. It'll be really obvious because there'll be an angle. But finally, let's do just some quick conceptual problems or semi-quantitative problems. If we had a graph here where we had force versus displacement, we wanted to know how much work was done. We can just use the force times the displacement from this graph. The area under the curve is always the y values times the x values. In this case, that's the force times the displacement, which is our definition for work. So if we do that, our work after 1 second would be, we've gone over 1, but up 0, so no work was done, 0 joules. After 2 seconds, right here, we have an area of over 1 up 2. I guess I should note that that's positive 1. Yeah, there. Now we have an axis. So we have 2 joules done. Then moving over, now we have a total of 4 joules done. Then here, this area here is actually -1 joule. So after 4 seconds, we have 3 joules total done. And then finally, after 5 seconds, we're still at 3 joules. I can use this information to figure out how much the energy changed. If I want to know how much this thing is speeding up or slowing down, then I know that during the first second, its speed wouldn't have changed. It had no change in energy. At second 2, it's now gained 2 joules of kinetic energy. After 3 seconds, it now has 4 joules. At second 4, it actually slowed down a little bit. And then at second 5, again, the force is the same, so it hasn't moved at all. Finally, last question, how much work is done after the mass falls half a meter? Well, to do this, I'm going to have to actually do some force problem stuff. I have mg acting on this block. I have tension pulling it up. Then for this one, I have tension. I have the force of gravity, and I have normal. Sorry, guys. So if I want to calculate what's happening here, one thing that I should recognize, this is frictionless, just for convenience sake. I should recognize that neither one of these can do any work on my system. The displacement of this 10 kilogram mass will always be left or right. Since it's moving left or right, and these are at right angles, neither the force of gravity nor normal force can do any work on it. The only force that can do work on it is going to be tension. So if I want to figure out how much work is going to be done, I will say it's going to be tension times that displacement of 0.5 meters. But I don't know the tension yet, so I can't finish this problem. So I'm going to keep doing the forces problem. I can say that my acceleration for my whole system would be mg minus t plus t. That's all the forces working in like this curved axis here, all over the total mass of 15. The tensions cancel because those are internal forces, and I just get 50 over 15, which is equal to, I think, 10 thirds. 10 thirds meters per second. Then I can go to, let's say, this object here, and say this object is moving with an acceleration of 10 thirds meters per second because it has a tension acting on it on that 10 kilogram mass. So then 10 times 10, that works out that I have a 100 over 3 Newton force times 0.5 meters for a grand total of 50 thirds joules. Okay, I know that was fast. Rewatch the video, see if you can work any of that out. I hope this helps clear up stuff on work. Last thing I need to say on work, though, is that there are two different things that come up on work a lot. We can talk about the work done by a specific force, and we could talk about the total work done on a system. If we're talking about the total work, we're going to say all of the forces, the net force times the displacement. If we're talking about a specific force, then we're only going to use that force. So for example, if we talk about me pushing a block at constant velocity across the ground, I'm pushing it forward with my force. If it's going at a constant velocity, that means there must be an equal force of friction going the opposite direction. That means on the block, since it's going at a constant velocity, its energy isn't changing. So the total work done on it is zero, which makes sense because the net force on it is zero. But that's different than how much work I'm doing. The work that I'm doing on the block would be whatever force I'm applying times displacement. And then we're talking about differences between what the change in energy of the object is versus what the change in energy that I'm trying to put into the object is. So that's all about work. I hope